Good morning. Welcome to Math for QFT. So in the next 5 lectures, we're going to discuss a number of different mathematical topics which have been chosen due to their relevance to the QFT courses you'll take later in the year. Both the QFT1 and QFT2 core courses, as well as some of the elective courses will use some of these, the mathematical topics we'll talk about. Almost everything what we're going to talk about will be used in QFT2. A number of the topics will be used in other courses, the other QFT courses, as well as a few non-QFT courses throughout the year. So that's the motivation for the topics I chose, and we will be jumping around a bit. So we'll be discussing 3 main mathematical topics, which are not necessarily mathematically so closely connected, but they're chosen for their relevance to QFT. So in this course, we'll spend approximately 2 lectures discussing distributions or generalized functions. So one example of a distribution or generalized function that's not a function is the Dirac delta. And we'll be discussing over today and tomorrow precisely what that means and how we can deal with objects like the Dirac delta in a mathematically consistent way. These types of manipulations will come up in our QFT courses. And then we'll switch gears and spend about 2 lectures discussing asymptotic series. So asymptotic series are another way that we can approximate a function. You're all familiar with convergent series. Sometimes we can't find a convergent series. And in fact, our main approximation method in QFT will give us, in general, an asymptotic series that is not a convergent series. And so we will discuss some methods for generating asymptotic series, the most important of which is the saddle point approximation, which will be one of our main techniques for perturbatively analyzing quantum field theories in the path or functional integral formulation, which we'll introduce in QFT2, and further aspects of it we'll discuss in the elective courses. And then in the final lecture, we will discuss it's usually called summation of divergent series. I put this in quotes because obviously if you sum a divergent series, you get infinity. That's what it means for series to be divergent. But nevertheless, there are mathematically well-defined ways in which we can assign a finite number to a divergent series. And that number can contain useful information about the original divergent series and we will run across many divergent series or divergent integrals in our quantum field theory courses, both from asymptotic series and also for our individual terms in the series. So just want to, in the final part of the course, we'll see, have an introduction to how we can assign finite numbers to divergent series, and see that it's not as entirely arbitrary as it might seem at first, and we can actually capture some of the information that the divergent series contains via a summation procedure. Okay, so that's at a very broad level where we're going over the next 5 lectures. And so for the first 2 lectures, we'll discuss distributions. And I just want to elaborate a little bit on what types of problems we can solve using distributions, or what types of mathematical questions we can answer using distributions that we can't with an ordinary function. So there's one example where you've all used a distribution. And that's a very important example in electromagnetism, is if we have a point charge, the charge density is identically 0 if the point charge is located at the origin. It's identically 0 for x not equal to 0, and it has some finite value, finite integral. We usually say that charge density is infinite at x equals 0, such that the integral, the charge density, is some finite charge. Now this is not a well-defined function. Infinity is not a number. We ask what is the charge density at 0. We can kind of wave our hands and say it's infinity, but that's not enough information to determine its integral. We need this extra bit of information. What's the total charge? That's, if I didn't write this, there's no way you could uniquely tell me what the charge is for this charge configuration. It's not a well-defined function. And for classical electromagnetism, that's not really a problem. But we're going to run into a number of situations in quantum field theory where we're going to need to manipulate objects like this. So this charge distribution is proportional to the Dirac delta, which is a distribution, and it's not a function because it doesn't have a well-defined value at 0. So the types of questions we can answer using distributions that we can't with our with ordinary functions and the usual rules of calculus for functions are questions like, what is the nth derivative of the absolute value function at the origin? Using the rules of calculus you learned in your first calculus course, you're not going to be able to answer this question. We can get an answer using a generalized form of derivation known as the distributional or weak derivative that I'll introduce. And so this is a question we can answer using distributions. We can't answer using ordinary functions. Another type of question we can answer is, what is the integral from minus infinity to infinity of dx over x? You might like to say this is 0 based on symmetry. We've got a, but if we look at this more closely, what we've got here are two divergent integrals. So the integral from minus infinity to 0 will give us negative infinity, and from 0 to infinity will give us plus infinity. You'd like to say that those can cancel out. And, well, in the simple case, maybe we don't need to be so careful, but if we have a more complicated case where we've got an ambiguous integral like this, where we have a positive and negative divergent contributions that might cancel, we might want to be able to approach it more systematically. And using distributions, we can answer, come up with prescriptions for how to deal with ambiguous integrals like this. Another very important application of distributions is for functional derivatives. So in David's course, you saw how to take the variation of the action to derive the Euler-Lagrange equations. So that is essentially taking a functional derivative. In quantum field theory, we'll be frequently taking multiple functional derivatives. And in general, a functional derivative is a distribution, not an ordinary function. And so I'll introduce, so the weak derivatives or distributional derivatives that I'll introduce will give us a very systematic way to evaluate multiple functional derivatives. It'll be entirely equivalent to what David taught you, but in my opinion, it's a more systematic way and an easier way to approach higher derivatives of distributions. And the final application is for finding Green's functions. So most of you are familiar with Green's function. So the problem for Green's function is you want to, if you have some differential operator acting on a function, you want to solve, one way to solve a differential equation is to find a function g that solves this equation, where if we act with the differential operator on the Green's function, we get the Dirac delta. As this equation involves the Dirac delta, it's perhaps not a surprise to you that Green's functions are in general distributions, not ordinary functions. And so at the end of this section of the course, I'll say something about how we can think about Green's functions in terms of the language of distributions. So that's where we're going. Are there any questions so far? Okay. All right, so as I mentioned before, we'll spend about 2 lectures on distributions. Today, I will introduce what a distribution is. And what we're going to find is that the best way to think about a distribution is it's a functional. It's a, we can think about it as an object that takes as its argument or as its input a function and outputs a number. So it's like a generalization of a function that has infinitely many inputs. And those inputs are what are called test functions. So during today's lecture, I'll expand on this way of thinking about distributions, and in particular Dirac delta, and why this is an important way, why this is a better way to think about distributions. And time permitting, I may start on the operations we can perform on distributions. This may be put off till tomorrow. So in particular, we can take derivatives of distributions, we can multiply them with functions, and we can compose them with functions. And so probably tomorrow, but maybe we'll start on that today. We'll see how we can act on distributions. And then we will look at the 2 applications I alluded to before. the functional derivatives, and Green's functions. Our most important example of a distribution that's not an ordinary function is the Dirac delta. And the way the Dirac delta is often introduced is as a limit of a sequence of functions. Where, for instance, we could take f sigma to be the top hat function, which is 1 over sigma 0 or 0, depending on if x is greater than or less than sigma over 2. This is a function that looks like and has the property that the integral of f sigma of x dx is 1 for all sigma greater than 0. So this sequence of functions approaches what we'd like to think about as the delta. It gets, as sigma goes to 0, it gets narrower and narrower, and more peaked around 0. And it has, for all elements of the sequence, the integral is 1, which is what we like the Dirac delta to integrate to as well. Nevertheless, this definition, we need to be careful if we think about the Dirac delta in this way. It's dangerous to think about the Dirac delta as having well-defined values at each point, as I alluded to earlier, and we'll see what kind of trouble we can get into if we use this definition without being too careful. Okay. So the claim is that the Dirac delta is not a function. And one way to see that is that, well, it doesn't have a well-defined value at 0. Another way we can think about it is we can try to define a space of functions and see if we can come up with a general enough class space of functions that contains the Dirac delta. And we'll see that won't work. So function space, so is a vector space whose elements are functions with a norm that satisfies the usual properties of a vector space. So it should have a positive norm. So for any function, the norm of that function should be non-negative. There should be a unique identity. So the norm should be 0 if and only if the function is 0. Should be a triangle inequality. Norm of f plus g should be less than or equal to the norm of f plus the norm of g. And should be homogeneous. For a complex number lambda, the norm of lambda f should be equal to the absolute value of lambda, the norm of f. So that's the usual properties we'd expect norm to satisfy for a vector space. And we'll see that, at least for simplest function spaces we can think of, delta is not contained in those function spaces. So one of the most important examples of a function space is the function space L2, defined on an interval AB. We're going to let A or B be plus or minus infinity if we like, to define it on the real line. And L2 is a function space that has the norm, or if you have a function in L2, the norm squared is the integral from A to B of the absolute value of that function squared. And so as long as this norm is finite, then the function so any f with finite norm is in L2 AB. Okay, so we see that this is a fairly weak condition, and so we haven't imposed any conditions on continuity or the existence of derivatives. So some rather wild functions live in this space. So it's a fairly broad, large function space. But we need to check that this function space fits with our definition of a function space. And in particular, we see that as we've defined things so far, the unique identity property is potentially problematic. And that's because, well, the claim is that a function space should have a unique identity, but it's rather easy to come up with several different functions in L2, as I've defined it so far, that both have norm 0. So in particular, the function that's identically 0 is 0. Yes?
What is L2?
L2 is the set of all functions where the norm is this, that have finite norm. So all functions with finite norm with this.
Okay. Is the integration Lebesgue or Riemann?
It has to be
Lebesgue.
Make it complete.
Yes.
Under the norm.
Yes. So this function that's identically 0 has norm 0. But so does a function that is 0, say, everywhere except at pi, and is equal to 27 at pi. This function also has norm 0. So if we want this to be a function space, we have to identify these functions. And any other function that has norm 0. So for this to work, we need to modify our definition of function space so that the elements of a function space are not just functions with a norm that satisfies these properties, but equivalence classes of functions. So a function space is a rather general thing, and well, if the elements of a function space are equivalence classes of functions, we don't need to have a well-defined value at each point, which was one of the problems I pointed out with the delta function, delta, which is the first reason I said that it's not a function. But we can have, in a function space, the elements be equivalence classes of functions, so that like the 0 element doesn't have a unique value at any point, because it's an equivalence class. We could come up with an element of the equivalence class that had any value we like at any point. That's still not, so L2, the elements of L2 are equivalence classes of functions, which are rather general things that don't have well-defined values at points. It's still not a general enough construction to contain delta. And to see why that is,
How are the equivalence classes defined?
so the equivalence class of 0 is defined to be all functions whose norm is 0. And if we take some other function, say the function x, if we're dealing with a and b are finite, then that would be an element of an equivalence class in L2. And we can add to x any function in the equivalence class of 0. Yes, Ian? The norm of the function. So in L2, the norm is defined to be the integral of the square of the absolute value of the function, or the square root of that.
When you write it without the square.
So we could just take the square root of both sides, and we take the positive square root. We want the norm should be non-negative. So and this is always a positive real number. Yes.
So when you're defining the equivalence classes, are you defining all of the functions with the same norm as the same equivalence class, or just 0 as one equivalence class?
So another way of stating it, so the definition I gave before was we take two elements, two functions are in the same equivalence class if they differ, if the difference between those functions is in the equivalence class of 0, another way of stating it is that two functions are in the same equivalence class if their values are the same almost everywhere, if there's a finite set of points where they differ. But those are the two equivalent ways of stating it.
A set of measure zero.
A set of measure zero.
Have to be finite.
Yes.
Rational numbers.
And so we can see that delta is not in L2 just by computing the norm of the top hat functions. So norm f sigma squared in the L2 norm is this integral integral from minus sigma over 2 to sigma over 2, 1 over sigma squared, which is 1 over sigma. And, well, the way first attempt at a definition of delta is just the limit as sigma goes to 0 of f sigma, which doesn't have finite norm. So delta is not in L2. Not, even though it's a very general function space, it's large class, large function space. It doesn't contain delta.
Calculating the norm, you find it as being the integral from a to b, so then why did you go from negative infinity to infinity when you were calculating the norm for the function?
Oh, so we can choose a and b to be any subs, or the range from a to b is a subset of the real numbers.
Right.
So usually we want to define the delta as a function on the real numbers. It would also the calculation wouldn't change as long as sigma over 2 is smaller than a and b. But we'd have the case where a top hat was, well, we'd have to modify our definition if our top hat was too large. Otherwise.
All the same vector space regardless of what a and b are.
So this is a set of vector spaces. We can define functions with different ranges.
Okay.
But really, there are three interesting cases: either where we're dealing with the whole real line, a semi-infinite interval, or a finite interval. Deal with those all those cases, or you can still call those L2 spaces. Okay, so why does this matter? So I just want to briefly illustrate one thing that can go wrong if we try to think about delta as a function. And so just to illustrate that this problem is more general than just trying to use this top hat functions as the sequence of functions that approaches the delta. Let's just assume we have some other sequence, or some sequence that could be the delta, or could be the top hats, or could be something else. So we'll choose sequence of functions g sigma such that the limit g sigma is 0 for x not equal to 0, and the integral of g sigma is 1 for sigma greater than 0. So that's the top hat satisfies those properties. You can construct any number of other sequences of functions that satisfy those. We could have triangles or Gaussians, something like that. And let's, so for each x and each epsilon, we can find sigma naught such that g sigma of x is in the following set of boxes for sigma less than sigma naught. And the boxes, so we can imagine we've got a sequence of boxes that gets progressively taller and narrower. So the bottom box has width epsilon, and each box is half the width of the box below it. And the height of all the boxes is 1. So for our top hat functions, we can choose sigma naught to be equal to the absolute value of x. Then for x, for sigma less than sigma naught, f sigma will be equal to 0. So the top hat will be we'll have width x, and so the point x will be a distance x away from that, but f sigma is 0 for x greater than sigma naught over 2. So that means that the top hat, the value of the top, regardless of x, we make sigma small enough, the value of top hat function will be 0, so it will be inside the boxes, it will be below the boxes. So that means that the integral, if we think about the limit as a function, so g here is the limit as sigma goes to 0 of g sigma of x. It has to be less than the area of the boxes, which is just epsilon plus epsilon over 2 plus epsilon over 4, or 2 epsilon. This works for any epsilon, so the area has to be 0, so this integral has to be 0. So that tells us that the integral of the limit is 0, which is not equal to the limit of the integral. So that's bad. The order of the limit and the integral matters. If we try to think about this limit as a function. And for those of you who have seen some analysis before, that this is related to point-wise convergence not being the same as uniform convergence. I'm not going to elaborate on that farther if you aren't familiar with those terms. Okay. Any further questions on this example? Yes.
What, you're saying 0 is not equal to 1, you're saying those aren't equivalent? Or?
That's right. So if we take the limit of the sequence of functions first, then I argued that we take the limit, this limiting function should have an integral which is less than the area of these boxes, which is, in this the area of these boxes goes to 0.
Right.
So this integral, this is the integral of the limit function. That has to be 0. But over here, if we do the integral first and then take the limit, then we get 1. Just because for everything greater than 0, by assumption, it's integrated to 1. Okay, so we've seen at least one potential problem that can arise if we try to think about the Dirac delta as a function. And well, a key part of this problem came from the fact that we were trying to think about the Dirac delta outside of the integral. So in other words, as long as we keep the Dirac delta inside of an integral, we're not going to, well, the claim is that we're not going to run into problems like this. So as long as we restrict ourselves to manipulations where we've got keep the Dirac delta inside the integral, we won't run into trouble. And we can think about this integral plus the Dirac delta as a map from a function to a real number. So if we integrate a function against delta, we'll output a real number. We can think of our input as being the function. And that's the basic idea. That's basically how we're going to think about distributions, is we're going to think of them as functionals. So that is functions whose inputs are other functions, and which output, in the simplest case, just a real number. So think about this as a map from function to real number. And so distributions are a particular type of functional. And the functions that distributions are allowed to act on are known as test functions. And so in general, the space of distributions you get will depend on the restrictions you place on the test functions. And the more restrictions you place on the test functions, the larger your space of distributions. So for most of the lectures and also during tutorial tomorrow, we will consider we'll place some very stringent conditions on our test functions that will allow us to have a very large space of distributions. And sometimes we'll need to modify the restrictions we place on the test functions, or in other words, our choice of test function space. But for many applications, we don't need to think too carefully about it. We'll see. I'll mention a few examples later where we might want to make slightly different choices. But for now, we will choose to consider the test function space to be C infinity functions. That means continuous with infinitely many derivatives. And we'll also require our test functions to have compact support, which means that they vanish identically outside a finite interval. Okay, so that's a fairly restrictive set of assumptions, and in fact, it's somewhat non-trivial to even think of a single example of a function like this. Can anyone come up with one? Yes.
Sine limited on one period.
Can you repeat that?
The sine function limited on one period.
Sine function. Okay, so we have the sine function sine of x for x between 0 and 2 pi. So we need this to.
It's not gonna work.
Isn't that a scheme?
Right. So the derivatives all have to be identically 0, where we match it on to it's identically 0.
Gaussian distribution will work.
Gaussian. So if we have e to the minus x squared, so that
Oh no, it's true.
it doesn't vanish identically outside of a finite interval.
All right. Yeah, I was thinking.
Does it have to be differentiable at the boundaries as well?
Yeah,
So it has to have infinitely many derivatives at all points everywhere.
so you can use e to the minus 1 over the absolute value of x, which is, because you cannot use any analytical function, otherwise it wouldn't have complex support. Yeah, this function is not completely supported, but you can use it to build one that is, because it touches 0 smoothly.
Yes.
So you can define a function that is 0 for x smaller than 0. It's this for x between 0 and. You'd have to use 1 over absolute value of x minus a, actually. Then it's going to be this function,
Yes.
x equals 0 to x equals a. Then it would be equal to 1 from a up until a b. Then you just reflect it.
Good. So for
This is the simplest case.
x yes between a and minus a and 0 otherwise. I think that works.
In minus a. You don't
Uh,
have it in minus a.
At minus, sorry, not minus a.
You can make the product with x plus a.
Yeah, you can use x squared
X
minus
squared.
a
X squared. Yeah, x squared. Right. So they do exist. It's not, as you've seen, it's not so simple to come up with examples, but yeah, so this is a very the reason I chose this test function space is particularly is because it's a very restrictive set of conditions, which will mean that we'll allow a very large class of distributions to act on them. Additionally, this choice has a nice feature of slightly simplifying some of the derivations. So that's another bonus for choosing this test function space. And probably won't use it very often, but I'll call the test function space D. And so distributions are functionals from D to consider the case where functionals map to R. We could generalize this and allow C or some other functionals to some other space. But for simplicity, we'll focus on the case where functionals map our test functions to the real numbers. And distributions are required to have three properties. So one is that it should be finite. That is U acting on any test function should be finite. So U is a distribution. And phi is a test function. Distributions also need to be linear. So that is if we act with U on alpha phi plus beta psi, we get alpha U of phi plus beta U of psi. Alpha and beta are numbers. These are test functions. It should also be continuous. So that means that the limit as n goes to infinity of U of phi n should be equal to, you can interchange the order of the limit and the action of the distribution. So the limit of U of phi n then goes to infinity is U of the limit of phi n.
What's the topology on D? Or do we evaluate that limit? The one on D.
So on D, so we need to put a norm on D in order to have a notion of when these converge. We could use the L2 norm, for instance, but this would this property will depend on the what distance metric we'll put on. For most practical purposes, these first two ones, at least for physics applications, these first two ones are the ones that might fail for something you might think about. This one is usually, at least for physics applications, it's usually not an issue. But, I don't know. I can't think of an example in a physics context where we could think of something we want to treat as a distribution that fails based on this property. Okay. And so I'll use two different notations. So one is the one you're more familiar with. So I'll often write an equation like this. So as I've mentioned before, this is slightly imprecise. We should not think about delta of x as a function. Nevertheless, thinking about writing it like this and keeping in mind that this part is the distribution is a useful way of writing it. And as you've seen here, the more common way I'm going to write things is as the action of a functional on a test function. So if our distribution is phi, then the equation would be delta of phi. It's phi of 0. In some of the references I posted online, I don't know if I mentioned this earlier, but the notes are also posted online. I'll post those ahead of time for all of the lectures. In some of the references on the wiki, you'll also see notation like this. I don't like this. This notation to me suggests an inner product. This is actually a pairing. These two things live in different spaces, so I'm not going to use this one. This one's better. Just in case you do take a look at some of those references. Yes?
I just can't see what that says on your notations.
Oh, it says the circled part is a distribution. Okay, so to make sure everyone's following and understands our definition so far, I'm going to give you 4 different functionals, and I'd like to you to spend a few minutes thinking about which ones are distributions or which ones fail any of our 3 conditions. Feel free to discuss with your neighbors, and then we'll discuss them as a class briefly. So the 4 functionals that may or may not be distributions are here's one possible, here's one functional, here's a second functional, which is phi of 0 minus phi prime of pi plus pi times second derivative of 7. The third functional, which is 1 if phi of 0 is 0 and 0 otherwise. And the fourth functional is the integral of phi of x over x squared dx. So take a minute for you to discuss with your neighbor and try to determine which of these are distributions, and if any of them are not, why not? Does anyone want to give us your reasoning for the first functional?
Not linear.
Not linear. Why?
Because a plus b, everything squared is not the same as b squared.
Okay, good. Good.
Well, no, but the test function is squared, that's important.
Right. Okay, good. Does anyone have any questions on this one? Did everyone? Okay.
How do we know if it's finite or not? How do we know if if the integral is finite?
Okay.
Complex support.
So, thanks for the question. So these functions are continuous and have compact support, which means that, so if we sketch a function, it'll be identically 0. A typical test function as a function of x will be identically 0, and has finite derivatives everywhere. So that means no matter what it's doing in the middle, in particular, it's bounded. The function is bounded. Every test function has some bound. We don't know in advance what that bound is, but all of these functions in our test function space do have a bound. So they.
Sorry, can simultaneously have the C infinity and the compact support at the same time to have them at the same time?
Yes, we can. One example of such a function is this function here. It's not too easy to come up with examples. I mean, the simplest ones are all basically look something like this, or superpositions of them. So we have a function which has so this integral has a bounded integrand, and it's an integral over a finite region. Therefore, it's a finite integral. So this one is finite. Any other questions on this one? How about the second function?
I just want so the topology should be very important, right? Because we just saw an example precisely where I mean, I'm sure you can bend the example that we did before to show that that U, if one doesn't understand the limit properly, to show that U is not continuous, right? We just saw an example where the integral of a limit is not the limit of the integral, right?
Right.
So definitely we need to choose a more stringent topology under which those limits wouldn't have converged to begin with, so that we could throw up that example and get continuity of U.
Yes. So the restriction we need to place on these on these sequences of functions is they have to converge with respect to a norm, or otherwise they have to be uniformly convergent. So point-wise convergence is not good enough. The second one, yeah. Any questions about this? Everyone happy that this is? Okay. How about the third one?
Not linear.
Not linear?
Why is it not linear?
Anyone to venture?
Functions that at 0 equals 0. If you have two functions that at 0 equals 0, their sum at 0 equals 0. So W of that sum equals 1, right? But by linearity, if it was linear, then W of that sum would be equal to 2. So it cannot be linear.
Good. Is there any other reason this fails?
I didn't check continuity, right? They have it.
That's right. Yeah, so we can imagine a sequence of functions that, say, approaches where phi of 0 is greater than 0 for every element of this sequence, but it approaches 0. So that would be an example of it. And assuming we could come up with a convergence series like that, which shouldn't be that hard. This also fails continuity. How about the fourth one?
It's not
I heard the right answer from someone who spoke very quietly, but not sure if everyone heard that, but it's not finite. Does anyone want to explain why?
take phi to be just one unity, and I think that's the integral does not merge.
Right. So phi is 1, doesn't converge. So 1 is not a test function, in particular because it doesn't have compact support. But we can make it into something. Well, all we care about for this example is what's going on near x equals 0. So we can construct a test function that looks something like identically 0 and match it on to something that smoothly interpolates to 0. We have a test function that looks like that, where we can use like this exponential trick to match function in different regions. So with test function that looks something like this, won't be finite. Good. Any questions on these examples? So in addition to the Dirac delta, there are lots of other distributions you already know. And particular functions that are locally integrable, which means this means that the integral from a to b of f of x is finite for all a and b. Are distributions where f at the end test function is defined to be the integral of f times the test function. So I'm being slightly imprecise here when I say that the function is a distribution. This is how people commonly refer to it, but if you want to be more precise, you could say that the functions induce distribution. So the object over here is a function. The object on this side is a distribution, which includes the integration against function. So this is the distribution, this is the function. It's common practice to use the same symbol for both, but just be aware there's a slight distinction in what we mean by f on each side of this equation. So that's another, in addition to the Dirac delta, many ordinary functions are also distributions, and that's the sense in which distributions are generalized functions. So they include many functions as special cases, but they also include objects like the Dirac delta, which fail to be functions. Okay, so now that we know what distributions are, let's see what we can do with them. And one of the first things we'd like to be able to do with a distribution is take its derivative. So, well, the first thing we might try to do to define distributional derivative is just use our ordinary rule for derivative. This makes sense for those distributions that are derivatives. Those distributions that are functions. We have a class of functions that induce distributions, and for those distributions we can make sense of this. It turns out to be, as far as I know, impossible to generalize this to include the other distributions. So, just because for we can't always make sense of the value of a distribution at a point. That's something that just fails to have any meaning, at least for some points for some distributions. So this is that's the first thing we might try. It's a dead end. And the reason this is a dead end is because if we try to use this definition, we're not using the fact that in general distributions are functionals. So we want to try to come up with a definition that uses the fact that distributions are functionals. So if we have the derivative of a distribution acting on a functional, well, again, we can take inspiration from the fact that we know that many distributions are functions. So we know how to make sense of this if u is an ordinary function. So if u is an ordinary function, we can write down this. And, well, we can manipulate this by integrating by parts. We get u phi evaluated at plus and minus infinity minus integral u of x phi prime of x. Now, here's where our restriction on our test functions comes into play. So this first term involves our test functions evaluated at plus and minus infinity. Now, we know that our test functions, by assumption, are 0 at plus and minus infinity, and in fact are identically 0 for outside of a finite range. So even if u blows up, phi goes to 0 faster. So this term is just 0. Because the test functions vanish outside of a finite interval. So this is the only term that survives. And this term we can rewrite as minus u acting on the derivative of phi prime, derivative of phi. So, and this is where our other assumption on the test functions comes into play, because we assumed that our test functions have infinitely many derivatives. So this expression makes sense. And phi, the derivative of phi is also a test function. We take the derivative of a function with compact support, it's still going to have compact support. If we take the derivative of a function with infinitely many derivatives, it's still going to have infinitely many derivatives. So this expression makes sense for any distribution because it's still acting on a test function. So even though we motivated this by considering u that was a function, we can take this as a definition for any distribution. So this is our definition of the weak or distributional derivative. And of course, we can do this n times, and I get the nth derivative. Of a distribution. It's just a factor that keeps track of how many times we had to integrate by parts for those distributions that were functions, and then distribution acting on the derivative of the test function. So any questions on this definition? Okay, so next time we will apply this and see how this allows us to, we'll both see that this matches our expectation for cases where we know how to take or can guess what the answer should be, and as well as some unfamiliar cases. And we will examine some of the other operations we can perform with distributions, namely multiplication and composition, as well as explore some of the applications of distributions to functional derivatives and Green's functions. So that's where we'll go tomorrow. Sure. Any other questions? Yes.
Still don't get why we are defining u prime phi as the way that you've written.
So this was a failed attempt. This doesn't work. U prime of this one. So u prime of phi. So if u is an ordinary function, then this is basically the definition. And in that case, basically there's only one possible thing we can do to manipulate this expression, which is integrate by parts. Move the derivative off u onto phi. You get a boundary term and this other term. The boundary term vanishes but because of the assumptions we placed on phi.
No, I get that. But do we define this in do we define the derivative in this form? Why do we define it specifically like this? Like, why do we have to integrate it with and have a product with the function?
So I'm assuming here that in this line, I'm assuming that u is a function, and functions induce distributions via the formula on this blackboard. Okay. Any other?
Why can we use this definition for distributions
Well, so if u is a distribution, then u of phi prime is defined. So this right hand side is defined. So we can so we can use it to define the derivative. It works, and it matches our expectation for the cases where we know what the answer should be. Okay. All right. I'll see you tomorrow.